All right, Internet, welcome back. So today we are going to do challenge number 3, and this is called coin flip. Now, as per usual, probably gonna catch a trend here. I'm in over my head. I'm in the deep end, but that's okay because I can cheat. And thank goodness for this guy's his series, because if Mr. Web3 blockchain developer didn't create the series, then I would have to do a lot of Googling and figuring it out on my own. But thankfully, he's created the series to help myself and you along, and hopefully the series I'm creating right now is also useful as well, because there's a lot of assumptions that he makes within his explanations, assuming that people understand certain aspects of certain things. And like I said, myself, I'm in over my head, so I had to do a lot of additional research into understanding specifically why there's a flaw within a contract. So hopefully this has helped you. All right, coin flip. Now this challenge, specifically, it's a coin flipping game. And in this coin flipping game, to complete the level, what we need to do is we need to use our psychic abilities to guess the outcome correct 10 times in a row. So if you guess it 10 times in a row correctly, then you can submit your instance and then you beat the level. And here it says basically the help that needs to be, like the hint they're giving here is basically going beyond the console. Because all the other historical challenges that we've done so far has strictly just been within the console here, putting in different commands and things like that and requesting certain aspects of the contract. Well, in this challenge, we're going to have to go a step further, and we're actually going to write our own attack contract. It's like a small script of an attack, and we're going to target the target contract with that script to then attack this so we can guess it 10 times in a row correctly. So with that being said, the weakness that we're actually exploiting in this is around randomness. So we can review the code first, maybe second. Let's review the code first, and then I'll explain specifically what we're exploiting. All right, so per usual, I put it inside of this setup here because it's bigger and easier for you to see. All right, we're gonna do the same thing. So we have our Pragma compiler here that's 6.0. As I've said many times before, floating point, not a good idea. It should be static, so it should just be this when you deploy it into production. Another thing is we have an import statement similar to last time. So we're importing safe math, and we're going to leverage that here as well as here. You can see we're calling the divider and the subtractor for that, so we can ensure that we're doing safe arithmetic inside of the contract. And I've included this bit here for myself just to know that this is slightly outdated, because you can see that the new import statement has utils. And also, in addition to that, I probably could touch this on later, but I'll do it now, is when we run this in production, we're going to have to run it through Remix to deploy the contracts. We're actually going to have to utilize 0.8. Reason being is it won't let us compile unless we use something newer for safety reasons. And also in 0.8 and above, and within Solidity, safe math actually is no longer needed because they've built in safe arithmetic inside of Solidity itself. So it's kind of baked into the language now. But that's neither here nor there. So we have our contract here. And in our contract, there's a few state variables we're establishing. So this first one here is basically utilizing safe math. So we're going to say, okay, for the uint 256 integers, we're going to utilize safe math on those. Here we have another integer that's going to be consecutive wins. So basically, how many times have we won this guessing game of the coin being flipped? Next thing is going to be the last hash. So you'll see where this comes into play later on. And then here we have a large number that's a factor. And you can kind of consider this as like the seed data for encryption. So with encryption, you usually have some random seed data that's placed into the hashing algorithm to create the kind of the safe, somewhat pseudo-random number that gets placed in there. And this is obviously not random because it's static and copy and pasted in here. So you can see that's kind of an issue already. So another thing here is we have our constructor. So per usual, we've talked a lot about constructors previously, so we'll kind of briefly explain this. So we have our constructor, which initializes the contract, the data within it. So the first thing that we're going to initialize is this state variable here. We're going to initialize it to 0. So when we start out this game, we're starting at 0. We need to get to 10 to win. Below that, we have our flipping function. So if we scroll down here, you'll see that the only function inside of this contract is the flip. Everything else is state variables or constructors. So if we look here, in this flipping function, taking in a parameter, which is Boolean, so true or false, and that's going to be our guess. This is a public function that returns a Boolean, so it's going to return basically the answer, is it true or false? Here, the first thing we're going to do is we're going to set up a variable, and that variable is going to be called block value. And what this block value is going to be is actually going to be the block number minus 1, so it's going to be the last block. So if we look at this, and the reason we're doing this is, let me kind of draw this out first. So if you're mining this block here, you don't know the block number because it's not established yet, or at least a block hash for it. And you can't hash a block number that doesn't exist yet. In addition to that, when you're creating this, you're actually calling back, and the minus 1, that's what that's referring to. So we're going to basically say we want the previous block number, we want then to hash that block number, and then once we've hashed it, we're going to turn that into a uint256 number. So after we've gone through these steps in this kind of order backwards, we're then going to put that in this variable. And next, we have a conditional. So we're basically going to say, if the block value equals the last hash, then revert, because that means that you're it's not unique. You're kind of basically repurposing the last hash that you've utilized, and that's where this variable comes into play. So that's helping us ensure that when we're creating these quote-unquote random generated coin flips, we're ensuring that the flip's not duplicating itself and repurposing itself, because if you do that, it's a lot easier to guess. So that's one condition. Some other stuff that's happening here is we have another value here. That's we're basically taking the block value and putting it into the last hash. So if we pass this condition, we're going to jump into this and say, okay, now that we've established this, we're going to put this in the last hash. And then when we've done that, we're going to then divide the block value here by the factor, so this big random number here. And I'm assuming the reason they're doing this is basically want to increase the randomness, or the quote-unquote randomness within this, by taking this massive seed number and then dividing it by the block value we've just established up here, and then putting that into coin flip. So when we do that, we're hoping that it's more random because we've added this random number for seed. Then after that, we'll take the coin flip variable we've created, and we're going to place it inside of another variable called side. So this is a tertiary, I think it's called I forgot what it's called. It's like a tertiary statement or something like that. It's basically a conditional like slapped into one little sentence. And specifically here you can see what we're saying is that coin flip equals 1. If coin flip equals 1, then true. Otherwise, false. That's kind of how to read these. And our goal here is to make sure that we get 1, so we get true, so we win. And it basically says here, so if side, the variable we just established, equals your guess, then consecutive wins increases. Return true. Else, consecutive wins goes to 0, return false. So if you guess correctly and your guess equals the side, then you up your consecutive wins. So you go from 1 to 2, then 3, 4, etc. And then if you guess incorrectly, then it's going to drop you back down to 0. So in a nutshell, this is the code, this is the contract that we're trying to exploit. And this function is obviously the area that has the weakness. Now, some of the areas that I'll call out that are weaknesses, and I'll point you towards some resources after kind of pointing these out, is first off, the randomness that they're trying to derive is on-chain. And let's actually take a step back, and I'll show you some resources right away. So here's a bunch of notes. Now, like I said here, this was a hard challenge. Thanks to this guy for helping me out. So here's a really good statement from the Mastering Ethereum book that I thought would kind of encompass this challenge in a statement. Now, the title of this section inside of the Mastering Ethereum section is that entropy is an illusion. Now, entropy, if you're not, a physics fan, is this like picture. I love this picture. It's so good. And in this picture, it kind of like encompasses entropy and a whole bunch of other shit. But entropy, in a nutshell, is something going from kind of an organized state where you have, things that are connected like this, and then over time, entropy occurs, and then it's dispersed. It's no longer organized and ordered. And that's similar to what's happening here with the Big Bang, where our assumption of what the Big Bang is. We started out very ordered, and then over time, you can see that the universe is expanding, and as expanding, more entropy is being created. And that's kind of the premise of entropy. So they're basically stating here in this statement that entropy within smart contracts is an illusion. And that's mainly due to the fact that within Ethereum, all Ethereum transactions are considered deterministic state transition operations. Now this term here is obviously quite convoluted, and I tried to simplify it, saying that for each input that we can determine which state the machine will move to. Meaning that if we put something into a contract, there's a good chance that we'll know exactly what's going to come out or what the state's going to transition to for the Ethereum kind of colossus of its collective mind space, I guess. And another way of thinking about this or explaining it is that all nodes run the same code and all nodes arrive at the same state. So this is deterministic in a sense. And I've also linked a bunch of stuff in here to help you understand some of these terms. So first things first is I recommend kind of reading just Mastering Ethereum here to understand specifically what the issue is and why creating randomness on-chain is a very hard thing to do. And there's a lot of flaws in it because people think that they're creating randomness by leveraging block hashes, block numbers, timestamps, things like that. But in all reality, either that's not random and it's easy to copy with an attacker contract, or it's potentially easily manipulated by miners because they have a control over certain variables that are encompassed within the block. And you can see that's kind of explained down here with the miners doing what they're doing here. So read that if you're interested. And some other links I put in here. So entropy, this is a friggin' amazing concept. So you should just read about entropy to understand kind of how chaos is created. Here's a great TED Ed video that explains entropy and what it means and how it works. In addition to that, this specific explanation is somewhat useful to understand deterministic machines, but also I've found a few diagrams to kind of explain what that means. So hopefully you can see these numbers. If not, I have another chart below it that explains something similar. But like I said, we know the next state of the machine and we know the input basically. So to explain that, we have a few different states. So we have state 0, state 1, and state 2, right? And then this is our input right here. So we're inputting something into the machine. So if we input 0 here, we can see that it's going to loop back on itself, and that's representing 0. If we input 1 here, we know that it's going to continue forward to the second state. So once we're in the second state here, if we input 0, we're going to go to the next state for state 2. If we input 1, we're going to go back to state 0. And then the same applies here. So if we're in state 2, we input 1, it's going to loop back on itself here. Or if we put 0, it's going to go back to state 1. Now, all this stuff is deterministic. We know exactly what's going to occur in each state, and we know if we put in a certain input, we know what the next state is going to be. So there's no randomness there. It's very, very deterministic. And if I scroll down a bit, you'll see another explanation here that's maybe a little easier to see because it's not black on black. So you can see basically we have our input here. We have state A, B, C, D. So in state A, if we put A, we're going to go to D. And if we're in state D, we put A or B, we're going to stay in D. And this is considered a dead state, I think it's called. You're kind of like trapped in this state here, and it's like an endless loop. In A, if you put B, then you'll go to state B. If you put B in state B, then you're going to loop back on yourself. Same here, so if you put A in state B, you're going to go to C. And if you put A inside of C, you're going to loop. And if you put B in C, you're going to go back to B. So like I said previously, all of this is deterministic. We know exactly what's going to occur because we know kind of how the machine functions. And for a random number to actually be truly random, you can't necessarily run that inside of an ecosystem that's deterministic like the Ethereum blockchain is. So there are a few methods that people are leveraging to actually get randomness and derive that. And there's also some serious weaknesses. So we'll talk about the weaknesses first. So if we scroll down here, you'll see that I've highlighted a few different things. So the old way of creating randomness, or at least the flawed way that people thought they were creating randomness, was using globally accessible variables. Now the important piece here is globally accessible, right? So everybody can see these variables and everybody can actually copy and paste your code and generate the same answer you're going to get and then send it back to you to get the win. And specifically, some global variables are timestamps, gas limit difficulty, etc. Another thing people utilize is block hash, but this is where the miner comes into play. And they can actually manipulate this as well. So another link, another resource to help you out with understanding what the global variables are and functions is the documentation for Solidity. You can see basically some of the main ones here. And you can see there's block hash, Coinbase, which is basically the miner's address, the difficulty, gas limit, things like that. So these are all accessible for all of us to interact with and visualize and utilize. So what's the issue here? Well, we can see specifically that in this contract, they're utilizing the block number, the block hash, which are both no-nos, right? We're not supposed to use globally accessible variables and functions to derive our randomness from. But in this contract, they assume that that's okay and that's correct. So if you look at the rest, we can see that generating the block value here, this is really the main flaw because they're doing it in a roundabout manner. And they're also putting in this factor, which is, no bueno because it's not random and you can see it and all that badness. So what we're going to do with our attack contract is we're basically just going to copy and paste this code here into our own contract. We're going to derive the same answer that they're going to derive. We're going to submit that in as our guess, and we're going to just keep winning over and over and over. And that's all we have to do to win this. So let me kind of go back here and make sure I've not missed anything. I'll come back to that method after we've beat this. All right, so this is the contract we're trying to beat, right? So I have the contract here written out of what we're going to do and how we're going to attack. In the other explanation, Web3 blockchain developer, he actually types this out for you. I'm not going to do that because I don't have multiple screens, so I'm not going to act as if I can memorize all of where this came from. I'm sure that when people do development on YouTube, they have one correct setup and one, scratch. And some people don't, maybe they're genies, but not me. So I'm just going to explain it to you. So in our attack contract, we can see it's named attack. And I'm going to show you this in Remix, but I'm just going to explain it here in VS Code, and we'll go to Remix and I'll actually deploy stuff. So first things first, as per usual, we need to have our Pragma compiler up, and then you'll see in Remix that we're going to actually have to change this to 8.0. Here we're importing a few things. In reality, we're actually not going to need this in Remix because we're going to be in 8.0, so we can actually use the native Solidity safe math kind of functionality. So our arithmetic is fine. We are going to have to import the target contract, which this is incorrectly named. It's going to be named CoinFlip, which is going to be there. And we're going to import that target contract so we can then actually utilize its target address to run the attack. So in our contract, we're going to name it CoinFlip attack. And then there's a bunch of comment notes here for myself, so you can kind of ignore that. I'll explain around it. So this piece here, we're going to establish a few variables, right? So the two variables we're going to establish are, first, we need to actually take our CoinFlip contract target up here, this target contract we're going to attack. We need to basically place it into a variable, and that's going to be our victim contract variable. So the next thing we're going to do is we're going to bring that random seed in here so we can utilize it ourselves, so we can get the same answer as the target. So we're going to put that in a variable. And the other thing here is we're going to create a constructor. So when this contract is initialized, we're going to actually put in the victim address, right? So that's when this contract's deployed, it needs to know specifically what address it's going to be pointing to when it's running its attacks and running its function to point out to the guesses basically and get the feedback there. So that's going to be our target address here for CoinFlip. Here you can see we're basically attaching that, so we can say we're going to call CoinFlip. This is going to be our victim address. We're going to put it inside of this variable, and that's going to be sitting here. So once we've done that, this is where all the magic happens, right? So this is basically us copying and pasting most of this code here inside of our attack contract, so we can just basically get the same exact answer they do and then send it back to them so we can win. So here we have a function called flip, and this function is, let's actually just get this out of the way so it doesn't distract you. All right, so public function flip, and it is a public function. It returns a Boolean option, so true or false. And we have a few variables we're going to establish here. So the first variable is block value. So this is the same thing I explained the last time. So we're just going to do the same process of getting the last block number. We're going to get the block hash of that, turn it into uint256. We're going to place it in the block value. We're then going to divide this by our random seed factor up here. And then we're going to put that in the CoinFlip variable. And once we've done that, we're going to do the same thing we did last time. So we're going to basically say, if the CoinFlip equals 1, give us true. If not, give us false. And then that's going to be our guess. That's going to be the side that we're going to guess on. And then we're going to place that guess inside of this call right here. So we're basically calling the victim contract. Remember, we've established that with the address here. We're going to call that victim contract. We're going to call the flip function, which is inside of the victim contract. And we're going to input our guess as side. And if we go here, you'll see that, oops, you can see this is the flip function we're calling from this specific section on that contract. And we're going to input our guess, which they called guess here. We're going to call it side here, which is fine. And that will hopefully give us our magical answer. So this challenge is a little bit time consuming, but we're going to walk through it together. So here I have our CoinFlip contract. So this is everything we reviewed already inside of the Remix IDE. And there's a few things you have to alter if you're going to do this challenge specifically, like copy and paste like I did. First, like I said, you're going to have to change the compiler to .8 and above because it's going to give you an error and not allow you to do anything. Additionally, when typing in your coin flip attack contract, I tried to open Zeppelin, and it basically told me not to. So I just changed the arithmetic from subtract sub and divide as div, and just basically put it as basic arithmetic. So block number -1 here, probably should be a space there. And then the divider was basically this divider here for that specific division piece there. So instead of using the div, I just used the divider symbol as like the basic solidity stuff. All right, so we copy and paste that in there. You make those minor adjustments to ensure that it actually works correctly for you. And then in CoinFlip, copy and paste this inside of there. We've had to adjust the compiler version so it would let us run it. Import math, for some reason, works fine here. I'm not sure why. Oh, maybe that's why. We're not using it inside of here. Internet, I just figured out why this doesn't work. All right, well, it works now, so I'm not gonna fuck with it. But if you wanted to, you could just import this inside of CoinFlip, and it should allow you to do the div and the sub instead of what I did here with the symbols. And it does this sometimes. It just goes dark. I don't know why Remix ID does that. So you just gotta refresh it. If your screen goes dark, just refresh. Yeah, so the point I just made, you can just import that and then actually use it, and then you should be fine. Idiot mistake. All right, so we have our contract, we've set up our attack, and now we just need to compile. So you can just do Control S or Command S to compile, or you can come here and say compile attack.sol, and then you can do the same thing for CoinFlip. You can say CoinFlip compile. And you can see there's some warnings here. So this warning's basically telling me the constructor is public, and that's a no-no, but it's just a warning, so we can kind of skip over it. It's not breaking anything, it's not allowing us to move forward. So we're good with that. So now that we've compiled both of those, we want to deploy them both as well. So CoinFlip, to deploy, you just go down to this little ETH symbol. And important thing here is we're going to want to inject Web3 instead of the other options. And that reason being is we're actually utilizing the MetaMask web browser. So we're going to inject that in here. So it knows that we're using the RinkP network. You can see that mentioned there. And then once we've done this, we're going to come down here. We're going to select CoinFlip. We're going to deploy CoinFlip. I can say confirm. Now, once this is deployed, we actually want to jump back to here to make sure we have the correct address for our contract. So if we do contract inside of the console, open this up, we can see in our ABI the different items that we've already discussed. So we have our constructor, which we've already touched on. We have the function of consecutive wins, and we have the function of flip. We've already talked about all that, but the really thing that we care about right now is getting this contract. The reason we need to get this contract address is because when we run our attack contract, we're going to specifically run that against our target. Now, if we come back here, that should be deployed. And to deploy this one, one thing, internet. I'm going to go backwards because I think this is important. I'm going to explain it. So specifically inside of this constructor here, there's one thing that we didn't do that you might see some developers do when they're doing a constructor, specifically connecting to an address or something like that, is sometimes before the contract they're calling, they'll put new. And then by putting new, you're actually creating a new instance of the contract. We specifically have chosen not to do that because we want to target the contract that's already deployed up in here in CoinFlip. And we want to actually continuously keep hitting the address so we can play the game and keep guessing the correct answers of that contract instance. So small nuance, but really important to point out here. And I've included it in my notes obviously here. So now we've compiled both. We want to go to CoinFlip attack, and then you can see here deploy has an address, because remember, we're not creating a new instance of this. We're going to this address. So it's specifically looking for when this contract is deployed, when we're deploying it, it's initiating or initializing an address we're going to put in there for a victim. And we're going to pull that from the console that we had here. So we'll put that there, we'll deploy, and we will send them all of our monies. And once this is established, we should get an option. And down here you can see the deployed contracts, right? So when running Remix, when you deploy something, you're going to have a section here that's called deployed contracts. And here you can see we've deployed CoinFlip, and we've also deployed our CoinFlip attack. So if we open up the CoinFlip attack, we have a function, right? So our function, we can basically call and flip. You have a victim contract as well. You can call this, and it basically shows you the contract of the victim. and that's going to match this one here as well. So if we call flip, we're going to then send them then our moonies. So when we send them our monies and we've flipped it, what's going to happen is we're going to go through this entire process like we've already discussed here. We're going to run this function. We're going to get our guess because we've run the exact same mathematics or the same arithmetic they've run here to get the random seed. We're going to then send that seed back to them in the flip function. So if I go to Etherscan, it's going to tell me it's still running, but I think we come here and we do consecutive wins, and we put that in there, open this up, we can see specifically that this has gone up to 1, and you've not seen it at 0, so sorry for not showing you that, but if we would have run consecutive wins here without running our attack contract on the deployed coin flip, this would have been 0, not 1. But now that's basically showing us that, hey, you've guessed 1 correctly. Congratulations. So now what's going to happen is I'm going to, skip over a bunch of time because I don't want you to watch me do this the entire time. But what I'm going to do basically is I'm going to iterate through this process. So I flipped it once, and I'm going to go to Etherscan and say, okay, that's a successful flip. I'm going to go back and I'm going to flip it again. So then I'm going to come here. I'm going to send the transactions once more, and it's going to go through the same process. It's going to say, okay, we're going through the process of mining the transaction in the block. I'm going to stay on the page and not do that. And I'm going to come back here, and I'm going to go like this. I'm going to say wait, come back here, open this up, and you'll see that now it's at 2 instead of 1. So I'll see you when I'm done. We did it. We did it. We made it through together. This is a game of patience. You have to do that 10 times in a row, and it takes not forever for the transaction to be validated and the block to be mined, but it takes a while. And if you're impatient like me, you're probably going to get a lot of errors. So if you send a transaction after sending in, if you flip, so basically if you flip and then you flip again too soon, it's going to give you an error here back on the block, or it'll sometimes give you an error like, I think transaction pending is another error I got back here. So just know, if you get errors back, it's because you're doing it too soon. You got to wait a little longer. So you can see here, if we flip long enough and we keep getting the right answers, as we should, we've gotten up to 10. So that means we are happy campers. So if we come down here and submit our instance, send them our moonies, that's gonna do its thing. So while that's doing its thing, I'm gonna come here and review the last piece that I wanted to that I've kept for myself that I wanted to share with you. So now that we know how not to get randomness via a smart contract on chain, there's a few methods of how you can get randomness that's a bit more secure, not fully secure, because I don't really think there's any true randomness on computers. Everything is quote unquote pseudo-random, but either way, it's more secure. And if you come down here, there's a few links I want to share with you. So first things first is this lecture here that kind of explains, not a lecture, it's a kind of a short video, talking through random number generation and gambling, and they explain a few different tactics of how random numbers are generated in the wrong way. But there's also another one here that talks through something similar. So this guy gives a lecture in, where is it? San Antonio? Santa Monica, California. And it's specifically talking through a project or a research project that he did. He got like 3,000 smart contracts from Etherscan and basically tried to find a bunch of contracts that had bad random generation inside of those, talked through some of the flaws, but also he talked through some of the ways to get good random numbers or more secure random numbers. That's another good one to watch as well. And I'll link in there the slides too. So there's the slides from OWASP where you can actually go straight to the slides instead of listening to the talk if you want to skip it. So here's some of the options, right? So one is commit reveal schemes. So a commit reveal scheme is very simple and kind of theoretically understanding it. So you have a person that's committing something, and then as time goes by, they'll then reveal it later once it's time to do so. So here you can see we have some sort of secret, or usually in our case, it's going to be a guess. So we're going to lock our guess in there in a secret safe that nobody can see. We're going to lock it with our private key. We're going to distribute that out to the public so everybody can know that we've actually committed something and we've made our guess, so everybody else can make their guesses now. So like here it says we'll wait for a little while, so for a few blocks to be mined by that time. And then once a certain number of blocks have been mined, then you'll finally reveal your guess. And then when you reveal that, you'll give your key out for people to unlock this box. Once they unlock it, then they'll see your guess or your vote in this case. And that's one way of actually mitigating miners either utilizing their power to manipulate the kind of the guess there, or others basically doing what we did, where we're just copying and pasting and getting the same answer with no time kind of incorporated into our formula. Here's a larger diagram that I pulled, and I kind of wanted to show this because it's a more in-depth understanding of what we just talked about above. So for this commit reveal scheme, here we have some stuff. So we have a user sends the ETH to the contract token factory. You're going to receive back a token. So you're going to come down here in the voting area. So you need your token to make a vote. So once you have a token to make a vote, you're then going to receive credits for staking tokens. I don't think that's relevant. Create a poll. So here we're going to create a poll, then we're going to vote inside of that poll, and we'll send our encrypted vote into this data structure here. So this is all encrypted and nobody can see it. So when the poll ends, which is basically as time evolves and blocks have been mined and things have evolved, they'll end that poll. So once the poll's ended, then this contract here is going to create a task inside of the Enigma network, and that task's then going to basically count up the votes and decrypt the votes so it can count them, and then it brings the results back. The poll is either rejected or passed. It's just a part of the contract, and then all that's done. So you can see that in this part here, between the vote and the poll ending, time has allotted, and then our vote was originally encrypted so nobody could see it, and then it was decrypted later on so they could actually count up the votes. So that's just another diagram that I found useful to understand intuitively what the commit reveal process looks like. That's one approach of actually creating randomness, utilizing time as a factor to help with that piece. And one important thing to point out about all these approaches is they're all flawed in one way or another. So there are weaknesses inside of this approach, and you can find those if you Google it. Next thing is using oracles off-chain. So oracles, they can actually go out into outside of the blockchain and get more hardened randomness. And that's usually a lot of the methods that we use today with encryption. So that's one method of actually just reaching out to an oracle, asking them to get randomness and bring it back for your chain to then present back to others. And this is a common thing that's utilized through Chainlink. They have their own method of creating randomness. And the last thing I wanted to show here is something I don't fully understand, but I have input a lecture here from Vitalik that I'll show you. If we just go to that really quick. This lecture I'll link into the description, but this is basically Vitalik talking through randomness for ETH 2.0, and that's going to be specifically on the Beacon chain. I think it's already being utilized on the Beacon chain. And it's basically leveraging on-chain randomness through combining two methods, because this method is slightly flawed, and I think this one may or may not be flawed. I'm not 100% sure, but if you combine them together, it actually gives you a stronger ability to create randomness. So definitely check that lecture out. And then the last thing is just a fun fact. I just want to show you this because I thought it was sweet and awesome. So Cloudflare, I'm sure many of you know it because it's basically the caching mechanism and the DNS provider, not DNS provider, but protector of many websites that you use. And Cloudflare, one of the ways that they actually create random seeds to input into their encryption process, because they have to create tons and tons of stuff, specifically for TLS and a few other reasons, they utilize lava lamps. Isn't that wild? So what they do is they have this wall of lava lamps, right? And in this wall of lava lamps, they have a camera, and this camera is consistently taking pictures of these lamps. And as it's taking pictures, each one of those pictures, every single pixel has an associated number with it. And every single one of those numbers are then strung together to create a really long random seed. And it's not just the lava lamps that play a factor into the randomness of the numbers for each pixel, but it's also the light. So you can see there's light coming in here, there's shading here. That light and shading changes over time, but it's really fascinating how you can actually utilize items like lava lamps to create a pseudo-random number, a seed that's incorporated into encryption. That's just that much stronger. So I thought that was pretty awesome. And then I linked here, obviously, their explanation to how it functions and how it works and why they do it. But yeah, so that is the challenge, people. We've completed the challenge, and let's go here to submit. Actually, we've submitted it. Let's confirm that we've won. Yes, level completed. We can go to the next level. I will see you on telephone.